Welcome to Chapter 12. Chapter 12 is all about Qt's support for writing multi-threaded applications. There are many ways you can do this in Qt, and we explore most of them. So with that, I want to jump right in using the very simplest, or I should say lowest level of the Qt threading models. We're going to use the Qthread. So Qthread allows you to take a QObject, assign it to a thread, and then have that thread run separately. There's also another way of using Qthread, which is to inherit from it and overload some of the methods. There are reasons for doing both, and if you want to get into one of the more interesting back and forth arguments on the internet, look up both ways. It really depends what you're trying to do. These days I tend just to create an object and move it to the thread. So here's a little calc function. It uses a fairly long running, in terms of things you can do on the computer, calculation, the QRandom generator 64. And in our main window, we can either start the calculation on a thread or not. We call this start calc method. If we say on thread, we then move it to a thread and start the thread. Always remember to start the thread. As late as a couple weeks ago, I actually was writing some threaded code and forgot to start the thread and spent far too much time, at least a day, almost a day, trying to figure out why things weren't running before I realized it. So if it's running it threaded, we create the object, we move it to the thread, and we start it. Otherwise, we fall through here. And once we've started it, which is done down here, we actually start the calculation. We then print a message saying calculation started. So let's actually go and run this code and see what happens. So here's our code. Now, right now we're set for 2000 loops. Now I want you to look for when that calculation started message box pops up. So let me hit run. Oh, the calculation's finished. Then the calculation started box popped up. Why? Because we didn't run it in a thread. So all the time was spent in that calculations object. And when the calculation object finished, then we got a chance to do our calculation started. So what happens if we run it threaded? Let's take a look at that. The message box came up immediately. Why? Because we started it and we immediately fell back into the next lines of code. All right, you're sort of probably wondering what's going on there. Why one? You got this little interesting piece of code here. I'm going to explain this quickly. We emit a message to cause the loop, the calculations to start. If we're in a different thread, auto connection will use a queued connection. If we're in the same thread, so we're running it in the run with this run button here, it will become a direct connection. So it's like a method call. It just calls right in there, runs it. So that's how we're able to see the difference. With a direct connection, the calculation is immediately started and we are stopped until it's done before we can run this. With an indirect, or with the queued connection, we queue it up, we display our message. When this method leaves, the message is delivered, the calculations start running. All right. So that is the simple, again, non-threaded, doing the calculations in a second thread. that allows us to have a much more responsive GUI. Alright, let me do a little cleanup here. Let's move on to our next level, thread pools. Again, thread pools, you create a thread pool, you create runnable objects, you assign those, and the thread pool takes care of figuring out how many it can run at a time, and is one runnable, finishes it and schedules another one and keeps scheduling them. So I'm going to set this as the active project, and we are going to run it. Now, we'll take our same 2,000 loops using the same calcs, and just sort of proof is of that. All right. I basically copy and pasted the code. I did not use the dry principle. I actually copy and pasted between the two. So let's run threaded. This is actually run threaded. We have 100 threads, and we're dividing them up into 20 at a time. All right, let's go. Now, that was a lot faster. In fact, it's so fast that I think it's really worthy that we make it 10 times slower, or do 10 times number of loops. Now watch the active thread count and the pool size. So there are 20 threads being run at the same time. And I encourage you to experiment a lot. What happens if we do this? Does the time change very much? I'm not expecting it to change because we only have 4 cores. Yeah, it's about the same, even though we had an active thread. And there's probably some sweet spot. Well, if we just do 4. Very small pool. It's a waiting pool, we'd say in the United States. Much slower. And for completeness, and I'm actually going to abort this early, and you'll see why, we'll run it on 1 thread. Huh. Surprisingly faster than what I expected. All right. Now because I enjoy experimenting, let's go and run this on the Raspberry Pi. So I am going to click the Run button and turn on the Pi display. And let's have a little bit of fun here. The same code. Again, 2000 was fairly fast. Oops. Okay, notice it's not nearly as fast. We're running about 3 seconds. Let me show that over here. A little bit smaller and hard to read. This actually says 3 seconds for 20,000 threads. But that was a pool size of 1. So let's go back up to a pool size of 20. So that sort of gives you the difference between a quad-core AMD A8 processor versus an ARM processor in the Raspberry Pi. But again, I think it's kind of cool to look at those things and understand what it means. All right, let's say goodbye to our display, and we'll close up this application. And let's move on to our concurrent, Qt concurrent library. Again, let's start out on the host. Oh. Ah. There we go. So this time, we're doing a little bit more work. We actually go through 4 examples in the book, and they're all implemented here. We actually talk about this in chapter 13, how to see that we're summing some numbers, or here we're summing random. Remember this for chapter 13 because we find out something very interesting, a way to optimize that incredibly. So, first thing we're going to do is look at our examples. The first thing we do with run is we actually just create, we run the method sum random 1,000 times, and we grab a future. It says, give me the result. You know, this is, I expect this to finish in the future. All right. Then we print some messages out. Then we actually use the mapped, where we actually use these as inputs. Then we use mapped. And you notice the real difference here is how we get the results. The mapped, map runs it, mapped applies it. It's a subtle difference. And then we use mapped reduce, or map reduce, to actually do all 3 of those here, run it 3 different times, and also produce a working average using this method. So let's see how they run. Function 1 returned, function 2 returned, oh, sorry, function 3 returned next, and function 2 is still running. Which makes sense because if you look at the values we used, $1,000, $6,000, and $500. So again, run, and we're still waiting for the final one to finish, at which point we'll update our progress. There is a bug in how the progress updater is done. I'll let you figure out how to solve it and what exactly is going on there. So let's look at map next. In this case, we're waiting for it to completely finish before we display anything. All right, and they all finished together. It took 16,818 milliseconds to run. Let's look at that code. So right here, wait for finished. And you can see the output right there. Okay, let's do the mapped example. Again, we have a wait for finished in this method. And we see the result vector there. All right, and finally, let's try the mapped reduce. Sorry, map reduce. Now, so as each one is done, it's actually calculating part of the average. I find it's worthwhile looking in here. And let me just prove that it's actually doing part of the average calculation. We'll put another QDebug statement in here. All right. And we'll stop it. And we'll rebuild and run it. Use this to clear your output window. Any one of these windows, click there to clear it. Let's do map reduce again. And you can see the averages are being printed as the items finish. All right. So we've looked at the way we can break up and execute things in threads using the three basic styles: Qt concurrent, thread pool, and just Qthread. All right. With that, let's move on to looking at synchronization. And what I really wanted to show you was how we can synchronize using QWait condition. So we created two objects here, two QObjects. One is our car object, one is our track object. When we run the track object, we'll say that we're running the track object. That's useful. And press 1 to start all cars, or A to start all cars. We will then start one car, or we'll start all the cars. So we'll look at the wake one versus wake all. And then we just repeat this loop forever. When we start a car, we run it. And we use this for every car. We just will instantiate several of these. We grab the lock, we wait for the track to say we can go. When we go, we take a random amount of time for our car to go around the track, and then we print the message that we finished. So let's actually watch that run. I'll make this a little bit more easily viewed. So let me start and run one car. Okay, so car number 36 started and it ran. Let's do that again. All right. Now let me start all of our cars. I'm actually pressing the character in the return. I didn't sort out why I wasn't actually accepting immediately, and I actually have to force the return. Something you can do if you choose to. You see this time all the cars started and they finished in different order. So 902 followed by 24, followed by 201, followed by 1, followed by 36. Let's do another race. They all start at the same time. Let's see what happens again in the second race. The order of finishing is 1, 36, 24, 201, and 902. And no, it's totally random. I did not plan it to come out numerically. So that is how you use QWait condition. I came up with this example because I thought it was a little bit easier than the ones I saw in other places, which have to do with reading I/O and switching. That's how you can use it. I wanted to keep it as simple as possible, and I thought this would be a nice little simple example. So anyways, thank you for joining me for this video, and thank you for taking the time to read this book.